Assalamualaikum warahmatullahi ta'ala wabarakatuh. We are from Group 7, which consists of 5 members, which is Wan Zulfakri, Muhammad Syaukilah, Muhammad Imran, Muhammad Amir, and me, Muhammad Afifidlan. Our project title is Failure Mode and Effects Analysis for Plate Type Heat Exchanger. These are the contents that will be covered throughout this presentation, which consists of introduction, literature review, methodology, results and discussion, and last but not least, conclusion and recommendation. I will be covering on the introduction part for this presentation. For the background of the study, I did highlight two main key points, which is FMEA and also the plate heat exchanger. FMEA identifies potential product or system failures and their effects on the performance. It can also be applied to our components assigned, which is the plate type heat exchangers, to prioritize preventative and corrective actions. The severity, probability, and also the detectability of each failure mode are assessed, and the data is used to plan actions to reduce the probability and effect of failures. For the plate heat exchanger, it works by transferring heat between two fluids via a series of metal plates that are intended to increase the surface area available for heat transfer. These devices are widely used in many sectors, including chemical processing, electricity generation, and also HVAC systems. The problem statement for this study is the first one: the plate heat exchanger is experiencing inconsistent heat transfer and is failing to maintain the desired temperature range, which leads to a decrease in the product quality and also increase the amount of waste. The second one is the plate heat exchanger is exhibiting signs of corrosion, fouling, and scaling, which leads to decrease of efficiency and also increase in maintenance costs. The third one is the plate heat exchanger is experiencing frequent leaks and seal failures. This results in unplanned downtime and also increase the maintenance costs. As for the objective of the study, first one is to study the background of plate type heat exchanger in various industrial usage, and the second one is to develop failure modes and effects analysis (FMEA) for our equipment, which is plate type heat exchanger. For the scope of the study, the first one is to understand the behavior of failure mode for the component in the plate type heat exchanger. Next, to perform FMEA for each component of plate type heat exchanger with its failure mode mechanism. Last but not least, to assess and evaluate the risk priority number, which is the RPN, for each failure mode.
Regular inspection on the heat exchanger is important to ensure safe operation of the machine, as any failure or malfunction can cause serious safety implications. Inspection should be conducted regularly to identify any potential safety hazards and prevent accidents from occurring. If potential problems can be identified earlier, the corrective actions can be taken on the heat exchanger to prevent any adverse effect which can affect its performance and efficiency. There are few factors of challenges and failures that could affect the performance of the plate type heat exchangers. First is fouling. Fouling is the accumulation of unwanted deposits on heat transfer surfaces, and this layer restricts the flow area and imposes additional heat transfer resistance, and this is due to the presence of deposits that cause flow rates to increase with greater velocity. Secondly is corrosion, which is a failure due to corrosion in plate heat exchangers are frequently related to the design of the equipment, service conditions, and materials of construction. Although the materials used are usually resistant, corrosion will occur over time. Corrosion, which includes spin holes and cracks, can occur due to general wear and tear. And next is gasket failures. All gaskets will eventually deteriorate over time. The environment in which they were produced and stored may contribute to the degradations, and excessive operating temperature and pressure can also shorten the life of gaskets. Therefore, to ensure safe and efficient operation of plate type heat exchanger, regular inspection is essential to be conducted, and this is to minimize downtime, reduce energy costs, extend the lifespan of the equipment, and prevent the failure discussed earlier from occurring. Method of inspection can be conducted as per below. First is visual and physical inspection. Fouling can be detected with physical inspection. Monitoring temperature and pressure are the best way to troubleshoot and detect fouling in heat exchangers. Due to their insulating properties of fouling, heat transfer can fall outside of operating specifications, and fouling deposit can also cause pressure drop to increase between the heat exchanger inlet and outlet, which indicate frictional resistance or blocked flow path. Temperature transmitters can be used to inspect temperatures of fluids passing through the heat exchangers, and temperature drops may indicate loss of heat transfers caused by fouling. Pressure transmitter can be used to inspect pressure drops between the heat exchangers, inlet and outlet. And flow meter can be used to inspect decreasing of flow rate that may be caused by build-up of fouling material in plates. Visual inspection also include of making sure the plate pack is tightened to specifications, carrying and guide bars are lubricated, ensure gasket appear undamaged, check pressure gauge at each end of the plate heat exchanger to make sure the pressure drop is within expected limits. The plates of the heat exchangers should be regularly inspected for corrosion, holes or cracks by dye penetrant testing. By using this method, even the finest hairline cracks in the plate can be made visible. This inspection method is usually done after cleaning, where the entire surface of each single plate is sprayed with a fluorescent paint. After the appropriate exposure time, the plate is rotated and thoroughly inspected under the UV light in the darkened test room.
Okay, so the typical standards that are being used for plate type heat exchanger are API standard 662. Second one is ISO 155471. These two standards covers the same things, which are the type of plate exchanger it covers, which are gasketed, semi-welded, and welded. And last but not least is the British Petroleum Standard GS1265, which specify the general requirements for mechanical thermal design and testing of plate and frame heat exchanger. So next is the equipment boundary, where in an article, equipment boundary is defined as the age or limit of the equipment defining components and interfaces with piping, electrical and instrumentation. So on the left picture here, is the typical boundary condition for the plate heat exchanger, where we can see inlet and outlet are not within the boundary, so they are not part of the analysis. And the table below here is the list of the components, in general components for the heat exchanger. And for our project, we can look at the right picture here, which basically shows the five components of the plate heat exchanger that are within the boundary for our FMEA analysis.
My name is Muhammad Imran and I will be presenting about related failure incident. So this is incident number 1, which happened in the refrigeration system industry sector. So what happens is that they identify the presence of ammonia in the branch cycle after running some tests from the branch cycle. So as a result, the plant was immediately shut down and secured by the operator. So the damage is major for the plant as it needs to be shut down, and the leaking ammonia poses a health hazard for the staff and the plant. So the factor for this incident is that the failure of the heat exchanger plate was caused by defect in the welding process that occurred during manufacturing. The exposure to the brine solution further expedited the failure, resulting in the development of a leak path. This leak allowed ammonia to seep from the welded channel into gasket channel of the semi-welded plate heat exchanger, leading to the ammonia contamination in the brine. Next, in this incident, what happened is that a part of a gasket was blown out from a flange on the plate heat exchanger, releasing ammonia into the machinery room. So the orange painted pipe carrying ammonia runs through the plate heat exchanger and is secured by a flange bolted onto the outside of the heat exchanger using 4 bolt washer and machine nut. The nuts on the flange bolt become loose, resulting in a gap between the flange and the gasket. This gap provides an opening for the ammonia to leak out. So the pressure of the ammonia gas caused a portion of the gasket to be blown out. So there is a strong possibility that the absence of the lock washer prevent the nut from creating a sufficient back pressure after installation, resulting in the nut not being able to maintain the specified torque as recommended by the manufacturer. So lock washer are used to prevent nuts and bolts from turning, slipping or loosening due to vibration. So the loosened nuts on the flange caused the gasket to be displaced and led to a leak of the ammonia.
Okay, so now we talk about the failure mode and effect analysis process flowchart. which basically starts with defining the assets, process, and subsystem for analysis, and followed by the identifying potential failure modes and consequences for each process. And we have to conduct a failure effect and cost analysis, and we will identify and rank the three parameters that are required, which basically the first one is occurrence, the second one is the severity of failure, the third one is the failure detection, which as we can see on the table on the right here, for the occurrence probability, the 10 defines the very likely for the failure to happen, and 1 basically define the unlikely, very unlikely of the occurrence to happen. For severity, the scale of 1 means there's no damage, the scale of 10 means that complete failure of the system, where for the detection probability, the ranking of 1 is basically means a very high likely the failure will be detected, and the scale of 10 means that there is no detection of the failure. So after we have evaluated and assigned the rankings for the three parameters, we will calculate the risk parity numbers RPN by multiplying the three parameters, and we check if the RPN within the limit or not. If the RPN is within the limit, then we end the FMEA analysis. If it's not within the RPN limit, so we have to take action to lower the RPN by adjusting one of the three factors so that the RPN is within the limit. So that's basically the FMEA process flowchart for the heat exchanger.
Next is the failure mode and effect analysis for the component plate of the plate type heat exchanger, and the function of the plate is to provide a large surface area for heat exchange between the two fluids, while also allowing them to flow through the heat exchanger without coming into direct contact with each other. And the potential failure mode with highest RPN, which is 210, is falling, and the effects of the falling, it can reduce heat transfer efficiency and increase pressure drop. And the potential cause for the falling is accumulation of deposits or contaminants on the plate, and the current process control is by applying filtration, and the recommended action is to do regular cleaning, use of falling resistant materials, and after the recommended actions have been taken, the RPN have been lowered down to 32 from 210.
So the second component that has been selected is the nozzle. The function of the nozzle is to connect the heat exchanger plate to the fluid inlet and outlet pipes. The failure mode that has the highest RPN is corrosion or erosion of the nozzle. So the recommended action for this failure mode is regular inspection and testing of the nozzle to check if there is any corrosion or erosion occur. And replacement are necessary when failure mode is detected. So this will basically reduce the RPN from 280 to 72.
So the next component, which is tightening bolt and nut for the plate heat exchanger, and the function is to secure plate assemble together so the fluid is not leaking. So the highest RPM from this potential mode, which is insufficient tightening torque, can lead to a leaking or loose plate stack of the heat exchanger. The potential cause might be because of human error or tool malfunction. Currently, the process control is to train proper technique of a use a torque wrench to tighten bolt and nuts to the specified torque value, and ensuring that the torque wrench is calibrated accurately and regularly. So recommended action on this is to conduct regular torque audit and review torque specification, and the responsibility is within the maintenance team. So after action taken, the RPN for this failure is reduced to 160 from 378.
The fourth component from the plate type heat exchanger that we have chosen to do FMEA are the gaskets. The function of the gaskets is to seal between plates to prevent cross-contamination. The failure mode that has the highest RPN number is improper installation. The potential effects of failure are leakage between the plates. Recommended action for this failure mode is to develop standard operation procedure for the installation. After carrying out this recommended action, the RPN number reduces from 315 to 60.
So here's the FMEA template for frame component, where the function of the frame is to provide a sturdy base and support the weight of plate pack assembly and protect the plate pack from the environmental factors. So from the analysis, corrosion of the frame due to exposure of corrosive environment has the highest RPN numbers, where the recommended actions is to do regular inspection of the frame for signs of corrosion and replace the corroded parts. After the action has been taken, it can be seen that the RPN number RPN number has been reduced due to the detectability rankings has been reduced to 4. And the second highest potential failure mode is the cracking or fracture of the frame due to mechanical stress, which has the RPN number of 180. And the recommended action is to do regular inspection of the frame for signs of cracking or fracture, and to do the replacement of the affected parts. And after the action has been taken, the RPN number has been reduced to 144, where it can be seen the RPN number has been reduced due to the detectability of the failure mode also.
In conclusion, this presentation have explained the FMEA study on plate heat exchanger. Background research on plate heat exchanger was conducted before making a failure mode and effect analysis on the equipment. After that, 5 critical components of plate heat exchanger was selected and conducted FMEA on it. For every component, the failure mode that has the highest risk priority number was identified and conduct a corrective action to reduce the failure mode risk priority number. So that's all from us. Thank you.